multi-stage amplifier or cascaded system, the overall voltage gain for the entire system, how you're going to find out? You will take the gain of individual stages and then multiply all of them. So it's the product of the gains. If stage 1 gain is A1, stage 2 is A2, and then you have stage 3, A3, the overall voltage gain is A1 times A2 times A3. When you do the circuit analysis on multiple stages of amplifiers, cascaded system, when you do the DC analysis, each of the stage has to be analyzed separately because they are isolated from each other through the coupling capacitor. What do you remember about treating the capacitor during DC analysis? It's open circuit. We don't take into account the capacitor for DC analysis. So when it's open circuit, all the DC analysis you can do individually, independently. And then, because of that reason, on the second last point where I'm highlighting, because of that exact reason, all the DC calculations are independent of the cascading. Treat each stage as one amplifier. But when you go for AC analysis, AC calculation for gain and impedance, interdependent. One stage affects the other one. The first one is independent, the other one is interdependent. If asked in the exam, independent and interdependent, if you try to look at the question quickly, they look the same, but these are totally opposite words, totally opposite meaning. Here's an example. Can you see slide number 63 on the screen? You see slide 63 on the screen? RC coupled BJT amplifier, is that the slide?
Yes.
How many amplifiers do you have here? Look, Q1 is amplifier 1 and Q2. What kind of bias? What is this circuit called for Q1? Let me highlight. What is this DC bias circuit? What is the name of this bias? Already forgot? It's a voltage divider. You have 4 resistors, R1, R2, and RC, RE, 4 resistors. The second stage is also a voltage divider bias. So between stage 1 and stage 2, see which is the connecting element, this capacitor C2. The output of stage 1 is going as the input of stage 2. When you do the DC analysis, capacitor is open. Therefore, during DC analysis, there is no connection between input and output. And the VCC is provided independently to both the circuits, both the amplifiers. So DC analysis you can choose and do individually. But for AC analysis, C2 is short circuit. So whatever happens in stage 1 will also eventually affect stage 2. If the stage 1 gain is A1 or AV1 for voltage gain, let's call it A1. And then for stage 2 voltage gain is A2. The total gain is A1 times A2. Here it is just showing a generic formula. AVT, T is the number of stages. So A1 dot A2 dot A3 dot and so on. You can join multiple stages in another way called cascode. The previous one was called cascade. This is cascode. The orientation is not the same. As you can see, the first one, emitter on the ground, common emitter. The second one, which terminal on the ground? Base terminal, RB, it says here. This is the base. It's a common emitter, common base combination. If you arrange like this and make 2-stage of amplifier, what you will get as a result is high input impedance. The voltage gain will be somewhat low. The load resistor here, the load is RL. If you have low voltage gain for the input stage, it reduces an effect called Miller input capacitance. It's an effect due to the capacitance which is not suitable in high frequency applications. So if the Miller input capacitance is small, in high frequency applications, this circuit will provide you a more stable and better output. Any questions about these two? No questions? So well then, this is an important one. One of the first important one for today. Is everyone on the Darlington circuit? Slide 65.
Yeah.
Yes, sir.
If you connect two amplifiers like this, the emitter of one amplifier is connected to the base of the second BJT. What you get as a result, we call this connection a Darlington connection. It provides a very high current gain. If you look deeply inside, you can see what is happening. First, the base current goes in. This is IB, and then you have IC. IE almost equals IC. So what is IC? IC is beta IB. So if the first transistor beta is beta 1, the IE approximately IC. If you call it IE1, it is beta 1 times IB1. Then this current, you already multiplied by beta. Right now you have beta 1 times IB is going as a base current in the second transistor, beta 2. The second transistor beta is beta 2. Emitter current of the first one became the base and then gets multiplied again. So the final current that is coming out of the entire circuit, IE2, equals beta 1 times beta 2 times the original IB. 2 times it has multiplied. Typically, what's the beta value? You have seen in the exam, sorry, not in the exam, example problem, 50, 20, 90, 100, 120, etc. So you take maybe 90 multiplied by 100 or 50 multiplied by 50. What is the final beta? You have a very large number. The current coming out of the emitter of the final terminal is much, much larger because of it gets multiplied twice. High current gain. What is the practical significance? High input impedance. So if you have high input impedance, what happens? Impedance is like the resistance. For a high input impedance, it is suitable when you do not want noisy signal to come in. So you can suppress a lot of noise. But we have to analyze this individually because on the next slide there is a loop equation. So let's see. I'm going to draw a few parameters here. Let's call the first one IE1. This is IE. Just draw it here. IE1. IE1 equals what? Beta 1 IB1. Beta 1 times IB1. So we can show you how the equation is derived. IB2 equals IE1, isn't it? IE1 is same as IB2. This became the base current of the second transistor. So let's call it IB sub 2. Doesn't allow me. IB 2. It's not Z, it's 2. Equals IE1. And then what is IE2? If I put IE2 here, the emitter current coming out of the second transistor, let's call it IE2, equals, can you use the equation and tell me what should I write? Beta 2 times IB2. IE2 is what? I write on top, beta 2 times IB2. And then what is IB2 again? IB2 is IE1, which is beta 1 IB1. So replace all the value. Instead of IB2, you can write IE1. Instead of IE1, you can write beta 1 IB1. So finally, what do you have outside, going away from the stage, total stage is beta 1 times beta 2 times IB1. If we call the product of beta 1 and beta 2 beta D, the final equation becomes like this for IE2. IE2 equals, I decided to draw near the picture so that you can actually see what's going on. IE2 equals what? Beta D times IB1. Beta D, D is coming from the name Darlington. IB1 is your original base current, the first one that enters the Darlington circuit. That's the final equation for IE2. Any question? If I try to do the loop with the next circuit, I'm on slide number 66 now. If anybody is wondering, is someone wondering what's going on? It is here. Darlington circuit, base resistor, emitter resistor. What's happening? Inner loop. VCC minus IB1 RB. And then what shall I write? Minus VBE1, which is 0.7. And then minus VBE2 minus IE2RE equals 0. Everyone understands this one?
Yes, sir.
Okay. So the current that comes in the beginning, before the Darlington, is the current IB1. The current that is exiting the final terminal IE2. Let me write that down as well. VCC minus IB1 RB minus VBE1. The first voltage drop for transistor 1 minus VBE2 minus IE2 RE equals 0. But we said IE2 equals beta D times IB1, right? So IE2 RE means beta D times IB1 times RE. And IB1 is IB, the main base current. If you write the loop and substitute IE2 for beta D times IB, IB is IB1 actually, you will get the equation for IB. It is also on the formula sheet. Don't have to remember. I mean, don't have to memorize, but I'm analyzing. The base current going inside the Darlington can be calculated by this VCC minus 2 times VBE, because they are the same, silicon, over your base resistor plus beta D times RE. For the emitter current, what is IE? IC plus IB. So IB and IC is beta IB, beta D IB. You can ignore only the IB term because it's in microampere, and beta D right now will be very large. You can approximate IE as beta D IB. So it satisfies what we showed in the previous slide. The current coming out finally is the base current multiplied by the total beta product. And for emitter voltage, because this one, the E is on the ground, VE is from top of E to ground, IERE, exactly Ohm's law. VB you can use, if you try to find VB at this point, VE plus VBE. Total voltage drop, VBE is now 2 times 0.7. And then let's see if we have an example to do. I have to go back to your Teams page, the Microsoft Teams. So have a look at it and let me know if you have any questions while I look for previous examples. In the previous semester, I believe there was a Darlington example that I showed in the class. So I'm searching for that. JFET BJT Darlington example. I'm going to show you an example. It's loading. And I have to copy to your collaboration space. Let's switch our screen. BJT Darlington. Where did I lose it? Right here. Emitter, fix, Zener. Okay. Let it be there. Can everyone see July 01 Darlington example?
Yes, sir, we can see it.
Okay, it's not July 01, so let's fix the name. Calculate the DC bias voltages and currents for the Darlington configuration. So it is worked out for you. I'm not going to ask. First of all, we have to calculate beta D. How do you calculate? Simply take beta 1 and beta 2 multiplied. So 1500. 5000 is your beta now. Imagine. What's IB1? It came directly from the equation VCC minus VBE1 minus VB2 divided by RB plus beta D RE. Comes to 3.16 microamp. I asked for different currents from the student. IC2, what's IC2? If you approximate IC to IE, we call it IE2. And IE2 is the final emitter current, which will be beta D times IB1. If you take 3.16 microamp, 3.16 times 10 power negative 6, and multiply that with 5000, I got 15.8 milliamps, 0.158. So quite a large current actually. If I ask BC1, what is BC1? I think, I'm not sure if I can zoom in, but let me highlight for you. This is the collector terminal C, right here. See how the two amplifiers are joined? The collector of amplifier 1 also joins with collector of amplifier 2. These two are common points. It's a common point. BC1 and BC2, the same. What is the voltage? There is no collector resistor. There is no voltage drop. So if you put a voltage probe at point C, the collector, you will sense directly the 18 volts. If you are given a problem like this in quiz or exam, you should look at the circuit. It's 18 volt. VE2. From which equation did I get VE2? E2 is here. Emitter 2. Which equation? Do you remember? Which one? From emitter to ground, what is the voltage drop? Ohm's law, IE2 multiplied by RE. IE2 is same as IC2. Now, 15.8 milliamp, you multiply by 390 ohm. 6.162 volt is VE2. VB or VB1, because the first one, how much? How much did we say? VE plus VBE, that's what I said. If you want to find VBE1, what is the VB1? What is the equation? 2 times voltage drop of VBE plus VE2. Do you understand this point? If you take VE2 and add 1.4 volt, because 1.4 is 0.7 multiplied by 2, you get 7.562, which is approximately 7.6 volts. What about VCE2? It is VCC minus VE2. If you look at the outer loop, VCC minus VCE2 minus VE2 equals 0. Therefore, VCE2 is this 18 minus 6.16, which is around 11.84 volt. Are there any questions about this example?
No, sir.
If you do not understand any part, you can always ask me. There is no problem in asking question, or when I ask something, you try to answer. There is no penalty for the wrong answer. We'll now go back to our lecture slide because the next circuit is even more interesting. So everyone, you kind of understand the Darlington. Now we're gonna look at a circuit called the current mirror. For the current mirror circuit, I have to zoom out a bit. Actually, you know, there is also a load here. There is a load. Maybe try to draw a resistor. It is not shown on this slide, but in the book there is a load, and then you also have a VCC, either another VCC or connecting with this. Current mirror circuit, it will provide a constant current in ICs, but which one is the controlling and which one is being controlled? As you can see, there are two BJT transistors. They are connected as if they are the mirror image of each other. When you connect a DC bias, there's an input current IX. At this junction, which I'm highlighting now, it will split in two parts. Which are the parts? Some will go as IC1 because it's transistor 1. Okay, IC1. Now, quite tricky with this program. I see it doesn't allow me to draw C. It's auto-correcting. Let's call it IC1. And then you see the other junction, what it's doing. Base current, because when it goes away, even at this junction, it is further splitting. What is the split? If we call this base current IB1, this is IB1, and on the right hand side, the junction splits the current into IB2. So far so good. Now there is a symmetry between these two transistors. Some parameters here are identical. For example, VBE1 is equal to VBE2 because of the symmetry. IB1 also therefore equals to IB2 because here the current comes in, they split in equal share. So IB1 is IB2. So you can say if IB1 equals IB2, we can say IX equals IC plus 2 times IB1. I just pick one of the currents. What is the typical value of the base current? Microampere. And IC is milliampere. IC is 1,000 times larger than the base current, usually. Or depend on beta, maybe 100 times larger. If you write the equation IX equals IC1 plus 2IB1, Can we ignore 2IB in the equation? Yes. 2 times a microampere, that will never affect or reach the level of IC1. Hence, before I write the next one, can I erase all these things now?
Yes, sir.
Okay, I believe somebody is recording. Yes. So you can, if you forget something, you can play back. I will erase so that I would like to clean up this area for writing other stuff. Ix equals IC1 plus 2IB. We ignore 2IB in the equation. So Ix approximately, I can write this Ix, and I'm going to put an approximate sign like this. Approximately. See, doesn't allow me. What can I do? Okay, Ix approximately, I see. I wrote vertically. You can flip it horizontally and you know what sign I put. And IC1, if you think of the equation, IC1 is beta 1 times IB1. So Ix is beta 1 times IB1. Beta 1 times IB1. Therefore, if you rearrange the equation, it becomes IB1 equals what? Ix over beta 1. I rearrange the equation in a form so that we now can look and see why one current controls the other current. Everyone got until this point? IB1 equals Ix over beta 1. So the base current, you are controlling the base current. What is IC1? IC1 equals beta IB1. Now if you try to change IB, beta 1 is fixed. What will you change? You want to increase the base current, right? If you want to increase the base current, what will you increase? You will increase Ix. How can you increase Ix? Usually, you might change the value of VCC because there's an equation for that. Ix is VCC minus VBE divided by Rx. You can change VCC, or you can lower Rx, or you can even put a variable resistor Rx here. So by changing Rx, you will change Ix. But what did we mention about IB2? IB2 is same as IB1. If you change IB1, it means you also change IB2, which means if you make the change in variable resistor or VCC, you change IB1, you also change IB2. When you change IB2, what happens to the collector current? IC2 equals beta times IB2. So by controlling the input side, you're also controlling the output side. Whatever current you are providing on the input side, it will show up on the output side due to the symmetrical nature, and both transistors, they have equally same base current and voltage drop between base to emitter. If you remember the input graph, not the output, this is VBE. VBE, and the current is IB. This is IB versus VBE graph. For a transistor, silicon transistor, what will it look like? VBE until 0.6, nothing will happen. But as you keep increasing, there will be a lot of base current. So something like this. As you keep increasing IB, you also keep increasing VB on the first transistor. Once you do anything to the first transistor due to the shared connection and symmetry, VBE2 and IB2 will also increase, and then IC2 will increase, and this is the load current. This is the load. So input changes, the load side also changes. This is called a current mirror circuit. Any questions?
No, sir.
You can also decrease. You want to decrease the load current, you decrease Ix. How will you decrease Ix? Just increase the value of Rx. If it's a variable resistor, just change the slide, the potentiometer, make Rx maximum, Ix will be minimum. This is how a current mirror circuit works. So the left side is called I control, the controlling current, and the right side is I load. I load equals I control because of this arrangement. There's another one, current source circuit. We will explore this in a bit more detail after the midterm because we have control sources. This is one example. You can build a constant current source with BJT and other elements. In this case, what is it? Here's a Zener diode. When the Zener turns on, you have plus minus VZ. VBE, when it's on, VBE how much? 0.7 for silicon. That is a fixed value. VZ is fixed, VBE is fixed. What is the equation here? VZ minus VBE minus IERE equals 0. That's the Kirchhoff's voltage law, this whole loop. Now let me draw the loop. VZ minus VBE minus IERE is 0. Therefore, IE equals VZ minus VBE over RE. If you see VZ is fixed, VBE is fixed, RE is fixed, you have a constant current IE and emitter current approximately same as collector current. So if you add a load there, you can provide a constant current source to a load. Here's an extra DC bias on the bottom. This one doesn't matter because the loop we are talking about is in the middle. If you want to change the amount of current, you have to buy a new Zener with another rating, or maybe you put a variable resistor. Then this is not a constant current source. This is a variable current source, but how much current would you like to provide on the load? That depends on your wish. Of course, within a range. Want to troubleshoot the BJT? This is the last slide of BJT chapter. If you want to troubleshoot, check the DC bias voltage. If not correct, check other things like power supply. Sometimes the power supply is not connected. And you must not forget to check the coupling capacitor between amplifier stages. While checking the AC voltage, if not correct, check the transistor capacitor and the loading effect for the next stage. Any questions? If we don't have questions, I would like for a few moments you can stop. I will now post the assignment solution. So general files, class materials, and then I'm going to create a new folder called assignment solutions, and then let me post the PDF file there before we move on. You should also get a BJT homework today because the BJT chapter is finished. So I'll provide assignment number 2. At the end of the class, you'll see the announcement. Solution to, I can't find it. Homework number 1. What is this semester? 2/2021, isn't it? Just give me a few moments. 1/2021. Okay. 2021. Maybe it's not ready yet. Oh, I see. I got it. Let me just put the right name. Homework 1. There you go. So it is now being posted. Already uploaded, I think. There's a PDF file, solutions uploaded. You can see it's in my own handwriting. Some of my solutions are in my own handwriting. Some I just typed. So are you ready for the next chapter then?
Yes, sir.
The next chapter is also one type of transistor. It is called field effect transistor. In short, I call it FET. It's a three-terminal device, just like the BJT. It's three-terminal device. But field effect, BJT is called bipolar junction because in BJT the conduction is a function of two carriers, electron and hole. So both polarities, they participate in the conduction of current. But for field effect transistor, it is not bipolar in nature, it's unipolar. Either you have electron participating or you have holes. This depends on the construction, which we will see today. And for the field effect, why is it called a field effect? There is an electric field which is established by charges present, and this field controls the conduction path of the output circuit without the need for any direct contact between the controlling variable and the controlled variable. So they are not really touching, but happening due to the field. Let's go to the next slide. Are there similarities between FET and BJT? Yes. Both are amplifiers. Both can be used for switching devices. And you can impedance match one stage to the other stage. Impedance matching circuit you can use. But there are quite some differences. FET is a voltage control device. BJT is current control. If you remember the equation IC equals beta IB, that tells you that the output current is the function of an input current. For the case of FET, it's not same as BJT. The output equation is dependent on some input voltage, so it's a voltage control device. If you compare the input side impedance, FET has higher input impedance compared with the BJT. But if you're talking about gain, BJTs have higher gain than the FETs. You learned about temperature variation. What happens when temperature changes? The beta of the BJT can change and it will mess up your output voltage and current. But FET, if you compare with BJT, they are much less sensitive to temperature variations. So for ICs, integrated circuits, FET is a much better application. And the last part says generally more static sensitive than BJT. What's a static? Static is the static electricity. You may have experienced it in your daily life, especially in the dry weather. You walk on the carpet, on the floor, you keep rubbing your feet, and then what happens? Static electricity builds up on your body, and then you touch a conductor like a metal knob of a door, you feel a burn and hear a cracking sound that is discharging through the metal. You may also see this when you are driving a shopping cart in the mall, and then you are walking along. Static electricity builds up on your hand. The moment you touch the metal part of the cart, you know what happens. So the FET is much more sensitive for static electricity. It can damage, especially one type of FET, which we'll mention, I think, today, MOSFET, or maybe not today. Here, slide 3. The basic name is JFET, and this is the main focus of our chapter. We'll study a little bit about the MOSFET. JFET means junction field effect transistor. MOSFET, FET, the 3 letters, they mean the same. MOS means metal oxide semiconductor. There are different types of MOSFET. One is called the D MOSFET. It's the depletion type, and the other one is called E MOSFET, enhancement type. Their construction is slightly different from one another. Can everyone see the JFET construction slide?
Yes. You can see
There
it.
are two types. There are 2 types of JFET construction. First, let me tell you what this is. This is called an N-channel JFET. So the main body of the JFET is made of an N-type material. And then there is actually a single P-type material here. It's wrapped around. There are 3 terminals. BJT also had 3 terminals. What are they? Base, emitter, collector. This one, gate, which is G, and then you have source S, drain D. The black strip is actually ohmic contacts, a metal or conductor which behaves same with Ohm's law, which means linear voltage current relationship according to Ohm's law. The drain is connected through to the N channel through the ohmic contact. Also, you see the source is connected to the N channel by means of this ohmic contact, and then the gate is connected to what? The 2 P-type materials together with ohmic contact. The dashed line means it goes behind the body. 2 P-type materials, not 1, sorry, there are 2. What else do you see on the picture? Between P and N, do you see a dark gray layer between P and N? What is this dark layer? The light gray is the material. The dark gray, if you remember what it is.
Depletion region.
Depletion region, yes. The N-type material takes up the majority, and this is through which the current will flow. So it's not bipolar, not 2 poles. For an N-type JFET, it's an N channel. We call it N channel. Electron is the main carrier of current. If you have a P channel, then it's the whole, but not both at the same time. An N channel is more widely used than the P channel. The 3 terminals are named gate, source, and drain. If you do not apply any voltage at all, just leave it like this. In the absence of any applied voltage, you see the JFET has 2 PN junctions under no bias condition. When you don't apply a DC source, it is no bias. Between P and N, you have a depletion region, P and N, depletion region. We have seen in the first chapter diode that when you have no bias, there's a moderate amount of depletion region. What is in the depletion region? In the depletion region, there is no free carrier. That's why Depletion region is unable to support any conduction. The basic idea of JFET, you must be wondering, okay, current flows, but from where to where? Is it from drain to source, source to drain, and what is the gate doing there? What is the function of the gate? You can look at this water spigot just for comparison. As you can see, the gate, what is the gate? It has a valve. You can open or close. What happens when you close the valve? There is no water flowing out. If you just release a little bit, there will be a little bit of water. If you fully open the valve, then there will be a lot of volume of water. So if you compare that to the function of JFET, gate, it will be controlling the amount of output current by some way, which we will see soon. Source, what is the source? Source is accumulation of electron. Normally, current flows from excess electron to less electron, means actually it flows from the minus sign to the plus sign. That is called electron flow direction. But before that, when all the textbooks were written, they taught that current flows from plus to minus. It is called the conventional flow. So when you have excess electron, what is the net charge? Source, negative, minus pole. Drain means where the excess goes in, that's the drain, that's the electron deficiency or hole, which means you have a positive charge. But when you see, look back, drain is positive, source is negative. Really, current flows from minus to plus, but conventional current direction is from plus to minus. So when you solve the circuit, current flows from top to bottom through the N channel. Any questions? Are there any questions?
For me, no.
No questions. So here it says the gate controls the width of the N channel, therefore the flow. How do we do that? The parameter is VGS. The voltage between gate to source is the one that will control the output, which we will see. Three basic operating conditions for a JFET. Keep the gate to source voltage at 0, VGS equals 0, and then increase the drain to source, VDS, increase from 0 to some positive value. This is one operating condition. Second operating condition you can have, VGS is a negative value, less than 0. You may have -1, -2, -3, etc. But it is minus. And at the same time, keep increasing the drain to source voltage to some positive value. And the third one is called voltage controlled resistor. In this part, as you keep increasing the voltage, the current keeps increasing. It's just like Ohm's law. Here, there's an explanation frequently asked in the exam. In the exam, you have not only problem-solving question, you also have essay questions, maybe short or medium essays, sometimes long. For a long time, I did not ask long essays, but you have essay type questions. So we may give you a graph or a picture and ask you to explain what happens during this and that. Here you see VGS is 0, gate to source is 0, VDS keeps increasing. So we use a variable here in this picture, we use a variable DC source, keep increasing drain to source voltage. As you can see, drain current ID goes through the channel, comes out as IS, ID is same as IS. Electron flow is actually from negative side to positive. So as you keep increasing the drain to source voltage, what is happening? Do you notice the PN junction now? The depletion region, what is happening? The depletion region has widened. They're almost touching each other. Keep increasing the VDS. The depletion region will keep increasing as well. At some point, these two dark gray areas, they will touch each other. What happens to the current in the meantime? Okay, I said depletion region will increase, width of the channel is getting less, resistance of the channel is increasing. But even though the resistance of the channel is increasing, the current will also keep increasing. Ohm's law, the more voltage, the more current, because you are increasing VDS. Because VDS is increasing, it still follows the Ohm's law. Here, now what happened? VGS kept at 0 volt and VDS continuously increased to a point, a positive voltage, where two depletion regions, they touch each other and pinch off the channel. The channel is blocked. This voltage value of drain to source, VDS, we call it VP, the pinch off voltage. Let me highlight it. At pinch off voltage, the channel is blocked. If you look at the picture, what do you think about ID? Do you think ID will be 0 when you pinch off the channel? Do you think so? It is normal to think that there is no current. It's normal to think ID will be 0. From a physical perspective, if you look at the channel physically, this suggests that the current in channel ID drops to 0. However, it does not. When you reach the pinch off voltage, ID will not become 0, but ID will reach a maximum voltage. Okay, sorry, maximum current. After that, if you increase VDS more than VP, what happens? ID will not increase. ID will stay at that level. It is called IDSS, the maximum drain current. Let's look at the next picture. Can everyone see the graph?
Yes, we can see it.
So we kept VGS at 0. This is constant. We don't change it. Fixed. VDS is here. X-axis. Keep increasing the VDS to a positive volt. Before you reach the pinch off, because V equals IR, even though the resistance is increasing, ID is increasing too because of increased voltage. So ID will keep rising. Okay, keep rising like this. And then when you reach the pinch off voltage, the channel is blocked. What happens? ID reaches the maximum level. We call it IDSS, saturation current. And then you further increase VDS. ID will not be 0. ID will not go up. It will maintain the level IDSS. So any further increase in VDS does not produce any increase in ID. It's saturation or maximum current referred to as IDSS. We need so many parameters for the characteristic equation. ID, the output current ID is given by IDSS times 1 in the bracket, 1 minus VGS divided by VP, and then the bracket is whole squared. Now, the second operating condition where we decrease VG below 0. Let's say this is -1. So we put a -1 volt. And VDS is the same. Keep increasing from 0 to a positive value. Same thing will happen. Depletion region will increase. At some point they will touch. There will be a pinch off. But what happens? Look at this graph. We start with the first characteristics. VGS is 0. So you increase VDS, and then pinch off is about to happen, right? At pinch off, you reach IDSS. Now VGS is at some negative volt, -1. When you decrease VGS and increase VDS, again current rises, but pinch off starts to arrive. earlier, and then VGS is -2. See what happens. Increase, but now pinch off already happened at a much lower value of the volt. Pinch off is becoming earlier and earlier. If VGS equals same as VP, the pinch off voltage, in this case -4, it is given in the problem. What is the value of VGS, VP, etc.? VGS is same as -4. What happens? No current at all. If you keep the gate source voltage same as the pinch off voltage, there is no current. It explains in the slide that as VGS becomes more negative, the JFET will experience pinch off at a lower VP. So in the first case, maybe VP was 5 volt. Now here as VGS -2, you're having pinch off at only 2 volts. ID will keep decreasing. At more negative value of VGS, you see what is happening to ID. In the first case, your maximum IDSS was 8 milliamp. At second case, you got only 4.5. As VGS became lower and lower, the output current level is dropping and eventually drops to 0 amp. The value of VGS, which is caused this to happen, is called VGS off. No current, the transistor is off, also called VP. VGS off has to equal to VP for the transistor to turn off. What happens if you keep increasing VDS mindlessly, like without any consideration? Can you put as much voltage as you want between drain and source? No. Like any other device, the JFET has its limit. If you have too much VDS, drain to source, the JFET will break down. And in that case, what will happen to ID? Let's say, let me clear this graph. Let's say 24 volt is the maximum it can handle. Now you increase to 25 volt, what will happen? It will break down and ID will go to sky like this, exponential. So breakdown current, a lot of current, like a short, it will likely be destroyed. ID increases uncontrollably when you break down the JFET. What is the other region? We talked about two regions. First, VGS is 0, increase VDS. Second, VGS is less than 0, increase VDS. The third one, voltage control resistor. So which one is the pinch off voltage in this? Which is the pinch off? Let's say this is the pinch off. Here all the pinch off is happening, right? What happens to the left of the pinch off region? If you interpret the graph, what are you going to tell me? To the left of pinch off, before the channel is blocked, how is the current behaving with respect to the input voltage? Is it behaving linearly almost? It's like linear, see, almost linearly before pinch off. So the more voltage, the more current. It is following exactly Ohm's law. We call the left of the pinch off point, the left region, we call it ohmic region, where Ohm's law is almost perfectly followed. Here you can use the JFET as a variable resistor. How? VGS will control the drain to source resistance RD. RO is an output resistance value. It is resistance value. RO is the resistance value with VGS set to 0 volt. So when VGS is set to 0 volt, there's a fixed value of resistance RO. RD is the resistance at a particular level of VGS. So RD is using RO as a reference in this equation. should be R0 because Vg is at 0. 1 minus Vgs over Vp whole square. I don't think this equation is on the formula sheet. And I can't remember of a problem that asked you to solve this. So what happens if Vgs becomes more negative? The resistance is increasing. That's why you have less and less current flowing through. Questions about the 3 operating regions? Do you have questions? Are there any questions?
No questions, sir.
No, sir.
So please read these slides. These topics are very important. It is asked in the exam frequently. And your exam, I think it's a combination of multiple choice and then answering questions. So part 1 is multiple choice. Part 2, you have to type in your answer. Some of them are problem solving, some of them are essay. The concepts are important for both parts. All the explanation I've given to you now, until now, based on N channel because that's the most common. But what happens in a P channel? You just reverse the current direction and polarity, everything you see. Instead of counterclockwise right now, current is going clockwise. So that's one difference. N is the outer two materials and the main is P channel. The main carrier is the hole with the plus charge. Instead of Ig coming in, it will go out. Id is same as Is. Ig is 0. Actually, the gate current is 0. Why? It has a high input impedance. Polarity and direction all reversed. The characteristic graph will look like this for P channel. Here, VDS, ID versus VDS. You can see it's a negative voltage. Everything is mirrored. -5, -10, -15. And VGS, instead of 0, -1, -2, we are going 0, +1, +2, +3. When VGS becomes more positive, the JFET will become pinching off at a lower voltage. And then depletion region will increase. Don't worry about the P channel too much. I don't ask anything from the P channel. This is just for illustration. So what is the symbol of the JFET? We talked a lot about JFET. What symbol should we use in the circuit? We know diode has a symbol, BJT has a symbol, therefore JFET must have a symbol. This is the JFET. If you are looking at MOSFET, D-type or E-type, it's different, but for JFET it's like this. The vertical black bar connects the gate and the arrow is always at the gate. Gate with the vertical bar, on top you have drain, bottom is source. The gate to source voltage we call VGS. The drain to source voltage we call VDS. And as you can see, ID equals IS. You saw that in the N channel, the same current is flowing through the same channel. So the drain current and source current, they are the same. Transfer characteristics. What is the transfer equation or the characteristic equation of the BJT? IC equals beta IB, linear equation. Beta indicates the relationship between input and output. For JFET, the input and output transfer characteristic curve is not as straightforward. It's not a linear equation. It's like this. I mentioned a bit earlier. Output current equals IDSS, saturation current, times 1 minus VGS, which is the gate source voltage, divided by Vp and whole square. You have a square term now. You have a square term, it is not a linear equation, it gets more complicated. For different values of VGS, Vp, and ID, you can actually take shortcut points and draw the transfer curve. Here's an example. Can everyone see the graph?
Yes, sir, we can see it.
See, what are the axes? You have to look carefully, okay? Y-axis is ID, milliampere. And on the positive x-axis, you see 0 to positive VDS. Also on the negative x-axis, VGS. We are talking about an N channel. So one of the region is you keep decreasing VGS below 0. On the right hand side, it shows for VGS 0, what will be ID. When VGS is 0, the drain current equals IDSS. Same. If VGS is same as the pinch-off voltage, in this case, for this particular example, VGS is -4. What happens at the pinch-off? No current. When VGS is -4 volts, what is the current? 0. Then there are two other points. If VGS equals VP divided by 2, what is VP, the pinch-off? Let me write down the VP for you. For an N-channel JFET, the pinch-off is a negative value. VP is -4 volt because that's where VGS is same as VP and no current. If VGS is half of the pinch-off, which point I should choose? -2, isn't it? Do you see the -2 point? I just mark it. When VGS equals half of pinch-off, ID will equal to 1/4 of IDSS. What is 1/4 of 8? 8 divided by 4 is 2 milliamp. So I drew 3 shortcut points now. First point, VGS is 0, ID equals IDSS, 0.1. And then VGS as same as VP, ID is 0. Third point, VGS is half of VP, ID equals IDSS by 2. If you want to draw this, you cannot draw like 3 points in a straight line because the square function is not a straight line. You have to draw a smooth curve. If you want the best curve, you should have 3 points, or you can have 4 points for an even smoother curve. Which one should I take next? If IDSS equals, if ID equals half of IDSS, which point should I mark? Half of 8 milliamp is 4. Here is another point. It is not shown on this graph. You know what is this point? When ID equals half of IDSS, VGS equals how much? 0.3 of VP. 0.3 of -4 is -1.2. So this is at -1.2. How we come with this solution? Again, look at the equation. First of all, in this equation, can everyone see the equation I'm highlighting?
Yes, we can see it.
In this equation, put VGS, the gate to source, at 0. If VGS equals 0, what happens to ID? This whole term becomes 0. VGS, right? This one. 1 minus 0 square, it's 1 square. 1 square is 1. ID became IDSS, which you saw in this graph. When VGS is 0, here VGS is 0 right here. ID equals IDSS, the saturation current. Now make VGS half of VP. What will happen? If you take half of VP and then VP is on the bottom, so 1 minus half square, 0.5 square, what is that? 0.25. ID becomes 0.25 of IDSS. Here is the case. At half of VP, 1/4 of 8 milliamp is 2. Now in this equation, you can say when ID equals IDSS over 2, what will happen? IDSS cancels out, and then 1 over 2, you will see that VGS will become 0.3 times VP. If you solve it, 0.3 times -4 is -1.2, about here. Any questions about the mathematical solution? Any questions? So let me ask you one question then. On this graph that I'm displaying now, which one is the transfer curve or characteristic curve of the JFET? The right side or the left side? Which blue curve is the characteristic graph? You've seen characteristic graph of diode and BJT. Which one is the characteristic graph of JFET or the transfer curve?
On the right.
No, it's actually on the left. Let me clear everything. This graph, this curve is the characteristic curve of the JFET. Sometimes I give an equation. I give the value of IDSS and pinch off point. You have to draw the graph. When you're taking online exam, you cannot draw. You have to tell me the 4 or 3 different points. This one is the characteristic of the JFET. How do you get a Q point? You know the characteristic doesn't change, but you get Q point from the circuit. Sometimes the circuit load line goes like this. Hold on. The circuit load line may be like this. Then when they intersect, this is the Q point. This is IDQ, and the bottom one VGSQ. Circuit, the load line starts from the positive voltage. So it goes like this. Biasing circuit, I'm talking about biasing. From some circuit, the bias is a fixed bias. So VGS is a fixed value. You can draw a straight line. That's the Q point. In the next class, we will start doing DC analysis as well, because whatever you did in BJT with the DC biasing and different circuits, it also applies to JFET. So how to plot the transfer curve? This is on the next slide here. On the problem or on the spec sheet, IDSS is given, VP is given. Solving for VGS 0, you get ID is IDSS. Solving for VGS at VP, you get something, right? If VGS equals VP, what happens? 1 minus 1, so 0 square, everything is 0, ID is 0. And then solve for some other values. So for the other values, I taught you 2 shortcuts. First, find at VP over 2, and another one, find at IDSS over 2. So you'll get 4 points very quickly to draw a curve. Example of a JFET spec sheet. You see what are some of the limits? VGS off. This is an N channel. I can tell this is an N channel. How can I tell that? How can I say? Look at the VGS off, which is the pinch off voltage. Here I'm highlighting. It is a negative volt. VP is a negative volt. That's why I know this is an N channel. For a P channel, it will be a positive voltage. IDSS is given on the spec sheet. The maximum IDSS here is 5 milliamp. Then some other parameters that you have to think when you design circuit with JFET. Noise, conductance, capacitance, etc. Another example of a spec sheet here. Absolute maximum rating. Maximum drain source voltage BDS is 25 volt. Increase more than that, you break down. Drain to gate, if you apply voltage from drain to gate, do not exceed this. See VGS negative 25. Forward gate current, how much the gate can handle, 10 milliamp. And temperature range for operating, that's quite high actually, minus 55 to 150 Celsius. 100 Celsius is already boiling point for water. Maybe this is a military grade application. There are different grades of electronics. You have consumer grade, the range is not too much. For life critical applications like aircraft and medical devices, it has to be better. Military application, even better. Case and terminal identification. So this one, let me ask you another question. This one is showing, it says P channel. Just by looking at the symbol, can you confirm this is a P channel or N channel, and how? How can you confirm that this is a P channel or N channel? Any idea? You have seen a symbol before, so right now you're seeing another symbol. Something is different. Which one is different?
The middle one?
The middle one, the arrow?
No, the line, the middle one.
Okay. Which
Like
line? 3, 2, or 1?
The 2.
2. It's different.
Mm-hmm.
Where is the arrow pointing? It's pointing away. That's the P channel. I showed you the arrow pointing inside the device. That is N channel. You can also tell by this, P or N. But the arrow is always gate. If it's going out, it is P channel. If it's coming in the device, it's N channel. Similar to what you have seen. NPN BJT, the arrow at the emitter going away. PNP, the arrow at the emitter coming in. The next class, I would like to keep this for the next class. MOSFET. Just a quick introduction. Similar characteristic like JFET, but some additional characteristic which make them useful in so many different type of circuit. There are 2 types, depletion and enhancement. Mostly construction difference. Let's leave the JFET at this point. We are a bit ahead. I'm gonna take the attendance. Is Min Luin U here? Mr. Min Luin U. Section 555. Not here. Is Balang here?
Yes, sir.
Balang is here. Tiravut?
Yes.
Napatra?
Yes.
Pakon?
Yes.
Rajay?
Yes, Achan.
Chonikan?
Yes ค่ะ
Michelle? Michelle?